Good evening, everybody. I thank the organizers of the virtual IHRS 2020 for this opportunity to present before you. I shall be speaking about artificial intelligence and sensors. These are my disclosures. We shall begin my talk with a look at the ubiquitous ECG. I would encourage everybody to take a look at this single lead ECG strip and answer or think about two questions. What can be seen on this strip? Where do you think this strip has been recorded from? The objectives of my talk are to give you an introduction to AI, the types of AI, what possible challenges are there, what are the success stories, and give a peek into the future using a looking glass. What is AI? AI is a set of technologies that allow for intentionality, that is, sensing something in the environment, reacting to it and see how that reaction goes. Intelligence, considering various inputs and arriving at a decision. And finally, adaptability, the ability to change in the future based on experience of previous events. AI has been there for a long time. It has gone through many periods of intense enthusiasm and many periods of disappointment. The present period seems to be one of enthusiasm, particularly because there are advanced computing techniques available, data is stored more often than previously, and there are supercomputers with the necessary capacity to perform computing tasks. Is AI relevant in cardiology? Does it matter to the clinician what the computer experts tell us, or is it something that's not in our field? Let me try and describe that with an example. Artia et al. In their paper in Nature were able to show that on the basis of a single 12-lead ECG, the ejection fraction of a patient could be predicted. They took ECGs of patients and created a training set with a combination of ECG and the ejection fraction. Once they trained the AI algorithm via a technique called machine learning, they then used a validation set where only the ECG was given to the algorithm and it attempted to tell you what the ejection fraction was. The results were truly astounding. The area under the curve for the validation set for the algorithm in predicting the ejection fraction on the basis of the sinus rhythm ECG was nearly 93%. Compare this to other common tests like the TMT or the pap smear, where the results of the tests are less than 90%. Another interesting fact came out was that in those patients where there was a difference between the AI-based ECG calculation and the actual ECG, the actual ejection fraction as calculated by a cardiologist on the echo, those patients who had a low ejection fraction by AI, but normal ejection fraction by echo, eventually went on to develop a low ejection fraction on follow-up. In a way, therefore, AI almost predicted the fall in ejection fraction. Now, this was then applied to certain protocols. The first one of which is probably the detection of asymptomatic LV dysfunction on the basis of the sinus rhythm ECG in the ER. In nearly 1,600 patients, it was found that the AI-derived detection of systolic dysfunction less than 35% performed better than the prediction by NT-proBNP, which is the standard of care for prediction of LV dysfunction. Similarly, it also aided in surveillance for declining ejection fraction in patients who are on oncologic medications like trastuzumab, which is known to cause cardiotoxicity. In remote areas like Uganda, this technique was used to screen for left ventricular systolic dysfunction on the basis of an ECG without an echocardiogram. And now this is being tested in 2 trials for detecting LV dysfunction in the general population using a single lead ECG based on the form factor of a digital stethoscope. So what did they do there? They took an input data which was very clear, namely the ECG, which was easily available and which is affected by a myriad of processes within the human body. They then also chose the output variable, namely the ejection fraction, which is consistent in its measurement, and from a data set where the ejection fraction has been measured accurately. They made the initial guess that perhaps the ECG will be able to predict the ejection fraction, and then they proceeded to train the algorithm with use of what are called hyperparameters to validate this. Once they created the algorithm, they used the validation set to check for bias, whether the algorithm was able to do it in the validation cohort, and then they used it in a cohort which was different from the original training cohort to assess the variance of the algorithm. This is how potential approach to evaluating the clinical utility of an AI-derived algorithm can be done. Let's use another example. The same authors then attempted to predict whether AF was there or not in a pre-specified period of time based on a single sinus rhythm ECG. And it was noted that when you had a single ECG given to the algorithm, you could predict atrial fibrillation with a confidence of nearly 87%. And if multiple ECGs were available, you could predict atrial fibrillation to the confidence of nearly 90%. And all of this on the basis of a single sinus rhythm ECG. Now, to utilize this in clinical practice, a case scenario was then shown where a 92-year-old lady with history of one previous episode of focal neurological deficit presented with a second episode. At both times, the sinus rhythm, the ECG at the time of the event was sinus. She had a lot of ECGs going back to her follow-up within the institute. And when all these ECGs were evaluated according to the AF prediction algorithm, it was found that there were multiple episodes in the past where she could have had atrial fibrillation, but no clinical event. And at the time of the clinical event, the sinus rhythm ECGs which were present were actually predictive of AF in the peri-ECG recording period. Interestingly, when she followed up and an ECG was taken, the AI algorithm predicted the presence of atrial fibrillation at that point. So this could be used to tailor anticoagulation and initiate anticoagulation without need to access costly screening techniques which are insensitive to the presence of atrial fibrillation. This then has been incorporated into a study, namely the Beagle study, which retrospectively evaluates patients on the basis of the EMR, confirms whether the ECG recorded shows history of atrial fibrillation, confirms using specialized processing techniques called natural language processing. This is also a form of artificial intelligence to confirm clinical characteristics and the presence of stroke. This then was used to initiate prevention for patients to monitor or start oral anticoagulant drugs. The results of this study are awaited and could potentially change the way we screen for atrial fibrillation in patients with cryptogenic strokes. Other unique applications include the ability to predict a heart rate corrected QT interval, the ability to figure out dophytolite plasma concentrations, and estimate blood potassium measurements from a single ECG. It has also been recently used to diagnose the presence of hypertrophic cardiomyopathy with a sensitivity of close to 95 and a specificity of close to 92% in patients less than the age of 40. Healthcare and cardiology in particular in India is skewed. Most of our population have a rural location of stay, whereas most of the facilities are available in the urban areas. Affordability is poor, with nearly 70% of expenses out of pocket. 47% in the rural and nearly 31% in the urban areas, healthcare is financed by loan and sale of assets. Nearly 63 million are faced with poverty due to healthcare expenditure alone. We also have a reactive approach to healthcare where we wait for the problem to happen before approaching a physician. Current state of research in the country for AI is poor, with a poor H value for all our AI publications. The only independent private sector company involved in AI research is TCS, with poor contribution from the so-called institutes of apex learning. Recent centers have been proposed, but there is no medical center of value in this particular alignment. In a model marketplace, the academia needs to be doing core research in these problems. They can understand the real world problems in our patients and need to have access to live industry data in order to be able to create algorithms of value. AI literature seems to be increasing by the day, but the assessment of it needs strict guidelines and precautions. Data remains the single most important asset in creation of AI-based algorithms and solutions. The quality of the data, if poor, will lead to poor quality algorithms, which then will harm potentially patients rather than help them. The model performance needs to be evaluated rigorously, and the models need to be applied to various populations, subgroups, and safety nets need to be placed in to prevent harm to our patients. Oversight on AI has recently been created. Guidelines for clinical trial protocols have been published, and there is a thought that just like medicine, AI algorithms and stewardship for the same need to be created. Security remains a big issue. The concept of differential privacy, where the individual rights are upheld, but the population information is available, and severe punishments need to be meted out to any transgressions of the same. From current existing solutions to a potential peek into the future, we live in the COVID era, and there is a discovery consortium which is ongoing, enrolling patients in order to imagine having an inexpensive 15-second screen based on ECGs for patients of COVID-19. This is based on the hypothesis that in animal models and in published studies, there is cardiac involvement in patients who have contracted this particular infection. Our voice contains certain parameters which can be analyzed using AI techniques and potentially predict hospitalization in patients with heart failure. Using specialized recording systems, ambulatory evaluation of systolic time intervals is possible, which can then provide us with a more on-the-go information about the patient's hemodynamic status. Micro and devices with high fidelity to record ECGs, which can be injected in via a needle, are being developed. The ECG recording from these devices seems to have similar fidelity as that of a routine 12-lead ECG. And potentially, these could be made up of bioreabsorbable materials, which can then dissolve after the required period of recording. Unique form factors with high recording capabilities to record ECGs on the go, and perhaps even record additional signatures of high frequency need to be evaluated. Electrophysiology depends on destruction of the arrhythmogenic substrate. An alternative view to prevent arrhythmias can be by improving conduction through areas where conduction was previously absent or where conduction is damaged to prevent arrhythmias is also under evaluation. In the EP lab, there are multiple modalities of information that the electrophysiologist analyzes to come up with a solution. Newer algorithms in machine learning, like the BART algorithm, can help in integrating all these modalities in order to help us come at a potential solution. Large databases of information, which used to be manually evaluated and data manually mined, can potentially be assessed using techniques of natural language processing, which may then save us man hours for purposes of optimizing outcomes. Governments are now releasing digital health blueprints, collaborating with companies to improve the health of their population, incentivizing them, and also offering universal coverage with digital health for their citizens. It's important that we are able to integrate this into our day-to-day clinical practice. Coming back to the ECG, which started it all, this ECG or this strip has been recorded of the abdomen of a pregnant woman. In fact, if you process this ECG some more, you will be able to diagnose the presence of additional signals within this ECG in the form of fetal ECG signals, complete with a P, a QRS, and a T wave there. Application of AI into these fetal ECGs may perhaps by 2030 aid us in the management of patients, tiny little patients with abnormal metabolism, electrical activity, and help us diagnose distress in them much sooner than we are doing right now. A veritable ambulatory form factor, which then captures the data, sends it for patient management and engagement with a provider, who then can connect to the patient directly or tell them to come into a hospital, is the dream. Given the vast majority of patients who seem to have challenges with pregnancy and need to improve both maternal and fetal outcomes, this is probably something that I hope materializes by 2030. In summary, therefore, I'd like to say that AI is scalable, cheap, and potentially life-changing. It has predictive value and can help us initiate prevention ahead of time. It requires a high percentage of data validity, needs to define the use case scenarios and the populations for its use. Legal and insurance implications, especially of the predictive power, need to be configured. And just like any other learning, iterations of the models need to be presented and kept up with in order to allow for better utilization of our experience as time goes on. Thank you.